Valerie Lensch, and my project was on Aptamer-directed synergistic drug delivery, and this summer I worked under the mentorship of Valerie in the Receptor-Mediated cell labs. So a common misconception about cancer are its symptoms. When you think of a stereotypical cancer patient, they're suffering from weight loss and hair loss and fatigue and nausea, but these are actually side effects of chemotherapy and not symptoms of the cancer itself. So in traditional chemotherapy, drugs are delivered intravenously where they travel throughout the entire body. And since chemotherapeutic drugs don't have the ability to exclusively inhibit cell growth of cancerous cells, they also damage healthy cells. However, using targeted drug delivery, we are able to deliver these drugs directly to the cancer cells and therefore minimize the side effects faced by cancer patients. So we are trying to use the characteristics on breast cancer in order to target these cells. Most cancer cells have HER2 receptors and hormone receptors, progesterone and estrogen, which can be used as targets. However, the second most common form of breast cancer is triple-negative breast cancer. And on triple-negative breast cancer cells, neither HER2 receptors nor hormone receptors are present, and therefore it is the worst prognosis of breast cancer. Our targeting molecule is an aptamer construct, oligonucleotide aptamer AS1411, and our construct consists of the aptamer, a peptide scaffold, which acts as a carrier for the drugs. So the aptamer is a single-stranded DNA, which binds to overexpressed nucleolin receptors on the triple-negative breast cancer cells. The aptamer is uptaken through receptor-mediated endocytosis. How this works is the aptamer construct will bind to the nucleolin receptors on the cell surface. Then an endosome forms and the aptamer construct is brought from the surface of the cell to the nucleus. While this occurs, there's a pH drop in the endosome, which causes the drugs to be released. At this point, the drugs can go to the nucleus where they will inhibit cell growth. Now there's another factor that affects cancer therapy, and this is combination treatment versus single treatment. This is a clinical study that was done on breast cancer previously, and they compared lapatinib and capecitabine used in combination and capecitabine used alone. So here on the x-axis you have time, and on the y-axis you have progression-free survival and cumulative survival. So the black line is the combination therapy, and the gray line is the single drug therapy. As you can see, as time progressed, there were higher rates of survival for patients who received the combination treatment as compared to the single treatment. However, this isn't always the case. When you combine two different drugs, you can get different outcomes or results. The first effect you'll get is an additive effect, where the effect is a direct sum of the percent inhibition of drug A and drug B. And here you have combination index, which is equal to 1. The combination index is the value that you get from comparing the ratio of the dose of the drug in combination and the dose of the drug alone. You can also get an antagonistic effect, and here the effect is less than the additive one, and you have a combination index which is greater than 1. Finally, you can get a synergistic effect, and here your effect is much greater than the additive, and your combination index is less than 1. What this means is you want to have a small combination index, because it means you can use a smaller dose of your drug and get a higher effect. One reason for the synergistic effect is that you can pick two drugs that target cells differently. So we are using Camptothecin and Doxorubicin, which are topoisomerase 1 and 2 inhibitors. Topoisomerase is an enzyme which essentially unzips the double helix structure of DNA in order to allow it to replicate. By using these drugs, we inhibit topoisomerase so the DNA cannot unzip and therefore cannot replicate, and this leads to cell death. This is a previous study that was done in our lab comparing Camptothecin and Doxorubicin, however done in a different cell line than the one we are using. When you have 1 Camptothecin and 10 Doxorubicin, you get an additive effect with a combination index that is equal to 1. However, if you use 15 Camptothecin and 1 Doxorubicin, you have a far more synergistic effect. Now it's important to know what these synergistic ratios are because in clinics, when they're doing combination therapy, they will often just give you the highest tolerated dose of each individual drug that the patient can take. However, this isn't necessarily the synergistic ratio, so you might be giving far more drug and not actually maximizing the effect you can get. My project goal this summer was to find the synergistic ratios for the free drug, the peptide drug, and our peptide drug aptamer constructs. So in order to measure the cytotoxicity of our drug constructs, we performed MPT assays. And the first step is to seed cells in a 96-well plate and allow them to incubate overnight. On day 2, the next step is to make drug solutions in different concentrations and combinations and to seed those with your cells. We incubated those for 72 hours. So after the 72 hours, we remove the drug and we add MTT dye. In the mitochondria of living cells, this dye is converted to formazine, which has purple color. So these purple crystals form when there are living cells. Then we dissolve the purple crystals in DMSO and measure the absorbance. So this is a picture of one of the MTT plates we did. And on the right-hand side, you have the control wells, and here you have the darkest purple color because there are the most living cells. However, as you go towards the left where there's higher drug concentration, the wells are almost clear as there are no longer many living cells remaining. So this is what we found for our combination indexes for the free drug in our cancerous cells. As you can see, any values between 1 and 4 for the molar ratios of Camptothecin to Doxorubicin were found to be synergistic. This shows that Camptothecin and Doxorubicin can be used synergistically in cancer therapy. The next step was to synthesize the peptide drug constructs. So our peptide is made of glutamic acid and glycine amino acids, and we have 10 of those. And then we use catalyst to facilitate a reaction with the hydroxyl group on the carboxylic acid to attach our drugs onto the peptide. Now we have to verify first quickly using a silica gel layer chromatography. So the doxorubicin and the peptide doxorubicin have a difference in their hydrophobicity, so they will travel different distances up the silica. So as you can see, the peptide drug that's reacted is here, and here you have the unreacted doxorubicin, and it has not traveled this far up as a doxorubicin because it is now reacted. We also verified this using mass spectrometry, and by analyzing the difference in mass between successive peaks, we can confirm that the reaction has occurred. So the difference in mass between this peak and this peak would be equal to the mass of one doxorubicin, and therefore we can find the exact number of doxorubicins on each peptide. We repeated a similar process for our peptide camptothecin conjugates and also found similar results where the reacted peptide camptothecin remained at the bottom, and the difference between these peaks was also equal to 1 camptothecin. So after this reaction occurs, you're left with this peptide drug, but also unreacted free drug. And so we purified using a C18 HPLC column. And the free drug absorbs onto the column while you can use acetonitrile washes to wash out the reacted peptide drug. So we repeated the same MTT assay using our peptide drug constructs and found that a 1-to-1 ratio of camptothecin to doxorubicin was the most synergistic. So there's a huge difference in the synergy of a 1-to-1 ratio versus a 1-to-4 ratio where you have a very antagonistic combination index of around 14. The final step is to add the aptamer onto our peptide drug. So we react the peptide drug with the aptamer, and then we purify using a G10 gravity column, which separates the peptide and the aptamer by molecular weight. And then we perform sodium ethanol precipitation, in which the DNA precipitates to the bottom and you can remove the supername. So finally you're left with your purified aptamer constructs. We verified this by running a denaturing gel. So in these gels, it separates the constructs by length or size. So here on either side we have our control aptamer that is unreacted, and here we have our reacted aptamer, and it's higher up because it hasn't traveled as far down the column, so this confirms the reaction. Finally, to visualize our the cellular uptake of our constructs, we performed confocal microscopy. And so this is on our MCF10A cells, which are normal human breast cancer cells. And the nucleus is shown in blue and the drug is shown in red. So there isn't much overlap of the drugs and nucleus. So it confirms that the construct is not being uptaken. This, however, is our confocal images in our MDA-MB231 cells, which are the breast cancer cells. And you can see a lot more overlap of the blue nucleus and the red drug, and this shows up in the pink color. So future work includes finally, we still need to determine the synergistic ratio of our actual aptamer constructs. And we also need to compare the cytotoxicity of our aptamer constructs with a similar construct that has a non-specific aptamer. So we hope that the research we are doing will build a new platform for our highly specific drug delivery with synergistic delivery of 2 different drugs to breast cancer, and we hope that this will be able to minimize side effects faced by cancer patients. I'd like to acknowledge my mentor, Nisha Pusuluri, for helping me this whole year, the Michigan and Cell Labs, the Military Chair Funds for funding my work, as well as the EUREKA mentors, Stephanie and Kelly, and the peer mentors, Chris and Megan, for helping me as well. Thank you. Any questions?
The 2 drugs that you chose to use to best inhibit the Topoisomerase 1 and 2, how did you choose those 2 drugs, and how did you know preemptively that they would be synergistic?
There have been studies done using those 2 drugs before, so we have seen synergistic effects using them, but not in the cell lines that we are doing.
And has there been any work done to find 2 drugs that might be more synergistic or have a better combination index or lower?
Yeah, well, people are trying a lot of different combinations. So the one I showed was with lapatinib and capecitabine at the beginning. So there are other drugs that also have synergistic combinations. Yeah.
Can you go back to your slide with the different ratios that was done in the previous work? Oh, right there. So, is it better if it's going for more CPT versus DOX? Am I reading that correctly?
Yeah.
So, has there been a study where it's just CPT only? Because from the initial, just looking at it, it doesn't seem like the DOX is doing much.
So if you had compared a CPT alone on here, I believe that, so when you have a synergistic value, that means that your effect will be greater than the drug alone. So if you had just camptothecin, it would be less effective.
Okay. I think that might just be a solubility issue versus actual synergism. Just because I know doxorubicin is much more water soluble versus CBD. Do you think it might be because of that?
I'm not sure. Yeah, I don't know. I have to look into it.
Have you ever tried doing that synergistic study with more than 2 drugs?
No, I haven't, but there are definitely studies on more than 2 drugs.
How do you think, do you have would this ever be something that you would want to experiment with these double negative breast cancer cells?
Not at the moment, because it's already a lot to get 2 drugs onto 1 peptide. But if we were to find chemistry that worked well, that could definitely be a possibility.